So I have a question. We have two. I don't understand here why we have two active legs. One is R1 equal to Rg, the other one is R2 equal to Rg. One of them is for temperature, the other one is for strain.
Can you allow me to explain what I've just written?
Oh, sorry, I thought that it's the explanation for what you said before. I'm sorry.
No, no. I'm just starting the second part of the class with this new configuration. This new configuration is one active leg. That is, we are using one strain gauge at the leg number 1. That is, R1 is equal to Rg. And an additional strain gauge that is placed on leg number 2. Okay. And this strain gauge is equal to Rg, so the same strain gauge that we use for leg number 1, but it is not bonded to the structure. It's just close to the structure. It is just feeding the temperature field only. Okay, so we can't say that there is a Wheatstone bridge with two active legs, but just one active leg that is using, however, two strain gauges, one in leg 1 and the other one in leg 2. Okay, once again, we are using this strain gauge, this additional strain gauge, just for, as we can see later on, to compensate for the temperature field. Okay, now if you go back to your strain gauge, to the Wheatstone bridge layout, so this one, okay, what we can say now is that R1 is equal to the strain gauge, so Rg. R2 is equal to the strain gauge as well. Okay, so if you would like to link the input tension, okay, with the flow current, the current flow in this upper part of the Wheatstone bridge, what we can say is that V, the input tension, is equal to V is equal to twice the flow, the current flow that is flowing through the strain gauge times the values of the Rg. Okay, just because we are having the same strain gauge, okay, in both leg 1 and leg 2. Okay, because the product Ig-Rg is related to the maximum power that could be dissipated, then this equation could be rewritten as twice the root square of Pg times Rg. We already discussed that. Okay, so how about the sensitivity with these different configuration? The sensitivity, once again, is equal to V times R over 1 plus R square times the number of the legs times the strain gauge factor. Okay, but now what? We already discussed that the input tension is not exceeding the maximum, the tension that is giving us the maximum power that could be dissipated. So it is equal to root square of PGRG. Okay, then R is equal to 1. Okay, just because we are having R2 equal to R1 in this case, from the electrical point of view. And then the number of lactic legs and is equal to 1 as well, because only the strain gauge 1 is feeding the strain, okay, the other is just for compensation. So the sensitivity here is equal to oh, sorry, already written there. Okay, 2 squared, then 1/4, that is R over 1 plus R square, then 1, then kg. So at the very end, the sensitivity is equal to 1/2 kg root square of PGRG. Okay. Okay, so why having this second strain gauge? Just from the yes, just let's wait for the question. But from the operational point of view, we are having a strain gauge on leg number 1 that is feeling the strain. On leg number 2, we have the second strain gauge that is feeling just the temperature induced strain. Okay, so if you remember, there is a summation with a change of sign of the strain of the change of the resistances. So the strain, the change of the resistance because of the strain of what is feeding the strain gauge number 1 is including both the physical strain and the temperature strain. To this must be take out the change of resistance because of the strain gauge number 2 that is feeding just the temperature. Thus, it is compensating what is feeding strain gauge number 1. So at the very end, what you got is that the overall change of the resistance is just taking into account the physical strain, the structural strain, because the temperature induced strain is compensated with this, let's say, configuration. The resulting sensitivity is there, okay? And if you compare that sensitivity with the one of using just one strain gauge, okay, as you can see, we are having less than half, okay, sensitivity. So we are paying the temperature compensation with a reduction of the sensitivity, okay. That is because if we are putting the compensating strain gauge in leg number 2, we are setting also the circuit efficiency to 50%. Okay, that's the reason why we have a reduced sensitivity. Okay. What about now if we are taking into account this very nice behavior of an additional strain gauge? If we put the strain gauge instead of leg number 2, we are putting that on leg number 4. Okay, so once again, if I go up to the vision circuit, yes, here, instead of using this compensating strain gauge in leg number 2, that is, instead of having this strain gauge in resistance R2, we are putting that in resistance R4. These are the only two places, by the way, to put this compensating strain gauge, because if you go back to this equation, these are the only two options that we can have in order to take out something from the leg number 1. Okay. So let's see what happens if we are now putting the strain gauge for temperature compensating on leg number 4. Okay, so let me write that. Okay. Just one active leg once again. Leg number 1 plus compensating strain gauge, temperature compensating strain gauge. Leg number 4, the same strain gauge as before. Okay, so once again, what is the differential of potential that is active between legs 1 and 2, as we did before? We can say that this is equal to the current, electrical current flowing through the strain gauge number 1 plus times the sum of the two resistances R1 and R2, that is equal to 1 plus R square PG RG. You have to follow just the same way of solving as we already had in when referring to the quarter leg configuration. Okay. Then sensitivity, once again, we are having R over 1 plus R square and KGP, and once again is equal to 1, just one active leg. Okay, so that is equal to R over 1 plus R square kg 1 plus R root square PGR. We can simplify a little bit. So at the very end, what we got is that the sensitivity in this case is R plus over 1 plus here R kg root square PGRG. Okay. So what we found out is that by placing the compensated strain gauge instead of leg 2 on leg 4, we got the same high sensitivity as we got for quarter bridge configuration. And this sensitivity depends just on the circuit efficiency, R over 1 plus R. Okay, so that's the reason why when using two strain gauges, we are using legs number 1 and 4. That's because the sensitivity is higher than using 1 and 2. Okay, because you can play with the electrical efficiency R over 1 plus R. If you are setting your second strain gauge in leg number 2, then you automatically setting the circuit efficiency equal to 50%. Okay, that's the reason why we are using two strain gauges always in leg number 1 and 4. So open your DNA code and input this information. When using two strain gauges with a Wheatstone bridge, the legs are always 1 and 4. Okay, the reason is that we are having higher sensitivity. So the way we are using the Wheatstone bridge is more efficient, is best than using the legs 1 and 2. Okay. Oh, the other comment on that is that if you want to pass the exam, then you have to remember that when using two strain gauges, 1 and 4 are the legs that have to be considered, not 1 and 2. If you won't pass the exam, just answer me that 1 and 2 are the two legs. Okay, and then you won't pass the exam. So please be sure to remember this. Yes. Now we are having two strain gauges, but just only one active. The second one is only for temperature compensation. Now let's see what happens when you have two strain gauges that is actually measuring the same strain. So N will be equal to 2.
Okay, so we want, so in this configuration, there could be a case where we want to compensate for the temperature. Like,
yeah, yeah.
Okay.
Instead of using, for example, the charts. Remember, how can you compensate for temperature? You have to do the data sheet, go to the data sheet, see the chart, take the measurement, and then remove something. Okay. If you don't have this chart, or if you prefer not to use that, then you can use two strain gauges, and then you have a self-compensation. Just using the Wheatstone bridge. No other information is needed. Okay. Just the appropriate use of the legs. So 1 and 4. Please open DNA code and remember 1 and 4 is the optimal choice if you want to pass the exam. Otherwise, you can choose whatever, you won't pass the exam. Now, let's see, for example, what happens if we are having first a full bridge configuration and then half bridge configuration. Let's start with the full bridge configuration. So full bridge configuration means that we are having 4 strain gauges. Okay, that is 1 for each leg. So we are having strain gauge 1, 2, 3, 4 in leg 1, 2, 3, 4. And will be equal to 4. Remember, when using 4 strain gauges, you have to be smart enough to bond these strain gauges in the right location of your structure, because you have to sum up all the signals and not checking out all the signals in order to have 0 output. Okay. Then what you're having is the input tension is bounded by the differential of potential given you by this IGRG that relates to the maximum power that could be dissipated as usual by this equation. Nothing new by now. Okay. Because we are using the same strain gauges for all the legs, what we can say is that little r is equal to 1. Everything, all the strain gauges are the same. And also the balancing condition is met. Okay. So what we got is the sensitivity is equal to, once again, r over 1 plus r square and kg 2 square pgrg, that in our analysis will be equal to 2 kg root square pgrg. Okay, let me write it with more emphasis. And as you can see here, we have a sensitivity that is more than twice the sensitivity that we can have when using just one leg, when using the quarter bridge configuration. Remember, if you go back to your notes, we're referring to quarter bridge configuration. The sensitivity depends on the circuit efficiency, and it will tend to 1, okay, when you are having lower R that is going to infinite value. So when using 4 active legs, the corresponding sensitivity is more than twice, if you want, okay, that sensitivity. And that is the reason why we are using a full bridge configuration, because sensitivity is the highest possible. Okay, and that's the reason why we are using that. And by the way, we also have temperature compensation by automatically, okay, without doing anything else. How about half bridge configuration? So for the same reason that we got before when looking for the temperature compensation, the half bridge configuration is referring to leg number 1 and 4. Okay, please remember that the sensitivity is higher when using 1 and 4. Otherwise, you won't pass the exam and the sensitivity is lower, however. Okay, so half bridge, what we are saying is a 2 active legs, that is R1 is equal to RG and R4 is equal to RG. Okay, then just to be sure. Okay, leg 1 and 4. The input tension and the maximum dissipated power is given you by this equation that you know very well. Okay, now we can't say anything about the resistance R2. Thus, what we got is equal to 1 plus R square PG RG. Okay, so sensitivity is equal. Once again, rewrite all the equation from the very beginning. And is equal to 2. So the result is that the sensitivity is equal to 2R over 1 plus R kg to square of PG RG. Okay, as you can see, the sensitivity is higher, okay, than the quarter bridge configuration, but it's not that higher than the full bridge configuration because we are having the circuit efficiency, okay, that could not be 100%, it could not be 1, unless we are going to have little r that is going to have infinite, okay. So the half bridge configuration is something in between the full and the quarter bridge configuration in terms of sensitivity. Okay. So what is the general operating condition when considering the Wheatstone bridge for strain measurement? You have first to remember that you are measuring the strain in just one point. You can use 1, 2, or 4 strain gauges at the same time for measuring the same strain. So this strain at that point. Okay. The closer are bonded the strain gauges, the better will be the measurement, the higher is the accuracy. Okay, because you are measuring the strain because of the change of resistance because of the same strain. Okay. You can choose, as I said before, quarter bridge, half bridge, and full bridge configuration. The quarter bridge configuration is the one with the lowest sensitivity compared to the full bridge configuration that is having the highest bridge sensitivity. Okay. The half bridge configuration is in between. Okay. It's not that higher than the full bridge, but it's not the lower than the quarter bridge. Okay. By the way, we proved that if we are using the half bridge configuration, we have temperature compensation. We can have temperature compensation by using, let's say, a dummy strain gauge. Okay. If you are placing a dummy strain gauge on leg number 4, that is a strain gauge that is operating close to the strain gauge on leg number 1, that is feeding the same temperature field without touching the structure, then you can say that there is a temperature compensation. Okay.
Can you consider that, even though it's a dummy strain gauge, you consider that accurate?
Yes, why not? It's up to you. So that is the pros. Now, that are the pros. Now, what are the cons of that? Okay, because according to what I've already said, it is better to use always quarter bridge configuration, full bridge configuration, because it's characterized by the higher sensitivity. Okay, the cost that you have to pay, that is the cons of these different configurations, is the complexity. Because if you need to have a number of measuring points, for each point you have to attach, you have to bond several strain gauges. Okay, and the electrical wirings, the complexity of the measuring setup start to become very, very important. Okay, so most of the time we are using quarter bridge configuration, or let's say half bridge configuration. Okay, only for very specific points in which we want to be more than 100% sure of the results, that if we would like to have a very high sensitivity in your measurement, then we are using the full bridge configuration. Okay, so pros, we have high sensitivity by using full bridge configuration. However, the wiring, so the complexity in real life is important, start to become very important. That could not be neglected, because you start to play with a lot of wirings, and therefore it will take a lot of time to set up everything. It will take a lot of time to check that there is no inconsistency, so data are all okay, no noise, no wrong measurements. Okay, and then you have to pay a lot of workers in order to do that. Okay, so there is a highest complexity. Okay, now let's, yes.
Can you explain one more time about temperature compensating? I didn't understand.
So when you are putting your strain gauge if you go back here in the first equation that I wrote today here, okay, if you put one strain gauge in leg number one, that is R1 is equal to the Rg, the strain gauge resistance, okay, and you bond that strain gauge on the structure, then let's assume that you have an additional strain gauge that you can put on leg number 4, okay. This strain gauge is just close to strain gauge number 1, so to the measuring strain gauge, but is not bonded to the structure, so it's not measuring any strain. However, it is measuring the equivalent strain because of the operating temperature. Okay. Now, if you measure the output tension E star, you can see from this equation that this output tension E star is given you by the difference of the change of resistance delta R1 and the change of resistance delta R4. Delta R1 is due to the actual strain and the temperature strain. Delta R4 is only due to temperature strain. Because we are measuring the same at the same point, so these two strain gauges are the same, temperature field is the same, these two strain gauges are the same in terms of kg and other physical parameters. So what we are saying is that automatically this Wheatstone bridge circuit is compensating the temperature effect, because the delta R1 because of temperature is equal to delta R4 because of temperature, and then because there is a subtraction sign, they are compensating one each other. Okay. We also prove that we can use the leg number 2 to have this kind of compensation, but it is not good to use that. First, because you won't pass the exam. Second, because sensitivity is very, very low compared to the same configuration as obtained by using leg number 1 and 4. Is that okay?
Yes, Professor, thank you.
Okay. Then when you attach these the two strain gauges to leg number 1 and 4, you have an actual half bridge configuration, self-compensating temperature configuration, and the sensitivity is a little bit higher. Okay. Now let's close the class with this final consideration. Let's assume that, for example, you would like to have the strain measurement of an operating jet engine, okay, around the case of the jet engine. Do you feel that stay, let's say, 2-3 meters apart from this operating jet engine is good for measuring or not? Just you in person. Have you ever heard what's happening when a jet engine is operating? Have you ever taken that? So when sometimes like this one, you can't stay close to the test specimen. Okay? If you are measuring the strain of this table, maybe there's no issue at all. If you are going to measure the strain of an operating jet engine, then for temperature field, for noise field, it is better that your operating conditions are far away. Okay, so distance become an important issue. Okay, and because of the distance, also the resistance of the wirings become important. Okay, when evaluating the change of the resistance. So let's see together as a final comment what's happening to your measuring chain when using Wheatstone bridge, in which the wirings are not negligible in terms of resistance. Okay, that happens when you are having a operating condition like the one that I told you before. So the Wheatstone bridge layout will be a little bit different. Now let's see together. Okay. Okay, here is how your Wisdom bridge is modified because of the presence of not negligible effect of the resistance of the connecting cable. So we have R1, 2, 3, 4 as the one that we got before. Now we are having RC. Okay, that is the resistance of one connecting cable. Okay, so we have two wirings, RC and RC, lower and upper. The effects of this connecting cable are mainly three. Okay, three major effects of connecting cables. Okay, these are first signal attenuation. Second, balancing. Wisdom bridge balancing, of course. And last one, temperature compensation. Okay, so let's face these three different problems. So, signal attenuation. So in order to take care about this signal attenuation, let's rewrite the overall resistance. So the what I call R1 is given you by Rg, that is the strain gauge resistance, plus twice the times of the connecting cable resistance. Okay, you can see that as an equivalent resistance here. We're referring to the first leg of the Wisdom bridge. So the overall resistance, that we can call that R1, is equal to the summation of everything. Okay, here as you can see there. So the resulting, oh sorry, this is Rg actually. Sorry. So please modify the value of the resistance as Rg. So R1 is equal to the summation of these two. So the change of the resistance that is measured by the Wisdom bridge is delta R1 over R1, that is equal to delta Rg over Rg plus 2 Rc. Okay. Of course, we are assuming that although there, the cables and their resistance is not sensing any change of resistance because of the strain. Okay. And we can rewrite that as delta Rg over Rg times 1 negative L, in which L, calligraphic L, is the attenuation factor. Okay, that is given by 2Rc over Rg divided by 1 plus 2Rc over Rg. Just simply put that and you can find by yourself the value of the attenuation factor. That has also an approximated expression that is much easier to remember, 2Rc over Rg. Okay, if, and that is sometimes verified, if 2Rc okay, is much less than Rg. Okay, as you can see, the attenuation factor is something that is removing the effect of the change of resistance because of the strain. If you go back to the previous formula, delta R1 over R1 is given you by the ratio that you are expecting, delta Rg over G, okay, times something that is less than 1, okay? And this attenuation factor, L, is related to the resistance of your connecting cable. How can you use that? So you can use this equation simply by itself. For example, let's have let's assume that we would like to have an attenuation factor less than 1%. So from the design point of view, for the test measurement design point of view, saying that L should be less than 1% means that L should be less than 0.01. Okay, that is that your ratio between RC over RG should be less than 0.005. Okay, and here is the way on using this information. So if you want to start a measuring campaign in those worst conditions, for example, the operating jet engine, okay, and you would like to have an attenuation of the cables less than 1%, then you have to be sure to use connecting cables or strain gauge resistance so that that inequality is satisfied. How can you choose that? You have just to look in your, let's say, shelf and see how many strain gauges I got. What is the basic reference resistance of those strain gauges? What are the cables? What is the length of the cables? And then see whether or not, because of that inequality, whether or not you have to change the cables or you have to change the strain gauge by using, for example, strain gauge between the set that are available. Instead of 120 ohms, go to 350 or go to 60, that's to 600, or go to 1000 ohms, okay, in order to choose the best option. Or you can also refer to cabling, wirings, and therefore choose the wires that are characterized by lower resistance. Okay. This corresponds to different costs, different time to operate your measuring circuit, so it is just a balance. But however, the choice of attenuation is the one that you have to design as test engineer in order to design your test activity. Okay. Then balancing, this is the first effect. Second effect on the balancing. Remember, the balancing are so that R1, R3 should be equal to R2, R4. Now R1 is equal to RG plus 2RC. R2 would be equal to R3 would be equal to RG. R4 will be equal, for example, to RG in a half bridge configuration. Example. Okay. So in this case, for the half bridge configuration, to take it as an example, what we are having is that the balancing condition is written as RG plus 2RC times lower RG will be equal to RG squared. Okay, that is RG squared plus 2RC over RG is equal to RG squared. Can you comment that equation? What is the solution of that? The equation?
RC equal to 0?
Oh, not at all.
Oh, no, sorry, R.
It will be, that equation will be satisfied is RC is equal to 0. That's right, but RC is not 0 at all because we are having connecting cable with their own resistance that has to be considered. So that equation is telling me that is not possible, could not be solved. That is, the balancing condition is not met at all. So the effect of connecting cable is telling me that the balancing condition could not be satisfied. Okay. And then for that reason, we have to introduce a different configuration. So balancing is not possible. Use of variable resistance in parallel with R2 could solve problem. Okay, but it is a different, let's say, a different measuring setup, something different that could be used and it is available. I'm not going to talk about that. Okay. Okay. Last effect, very fast, is on the temperature compensation. Okay, remember, let's assume to have a Porter bridge configuration, Porter bridge, plus a compensating strain gauge on the fourth leg. Okay, as we saw together. Let's have this reference condition. The change of the output tension with respect to the input one, remember, is given you by this equation. Okay, and as we already discussed, delta R1 and delta R4 are so that the temperature change of resistance are compensating. So only the delta R1 for the strain will survive. But now what happens? We are having delta R1 that takes into account also the connecting cable. So this is equal delta R1 to delta RG over RG plus 2 RC because of the strain.
Sorry, Professor, I cannot see anything on the board.
It will take just a second, it will come. RG plus 2. Okay. I hope that it will. So, however, when referring to that equation, you can see that delta R1, the change of the resistance, will be because of the strain that we want to measure. Okay, the change of the resistance of strain gauge, the change of the resistance of the strain gauge because of temperature. Okay, and also this change of the resistance because of the temperature acting on the connecting cables. On the other side, delta R4 is just due to the temperature effect. So that equation is not satisfied. That is, we are having an output tension not just because of the strain gauge, but just because of everything. So we can't have any temperature compensation at all when referring to their configuration, but with the resistance of the connecting cable that is important. Okay? The Porter bridge plus the compensating strain gauge are the four leg. Okay, the one that we saw together. We can't have. Yes, when we are not considering any connecting cable, yes, we can. But when considering the connecting cable, there are no compensating terms. As you can see on the notes that I, oh, here it is, here they are. Okay. As you can see, the delta R1 is